This video will discuss all 10 active volcanoes within the state of California, even the lesser known ones, with each volcano and their last eruption being discussed beginning at the timestamps shown on screen. Enjoy! While what you are looking at might initially appear to just be a nice 9-hole golf course with a central lake, it is in fact much more than that from a geologic sense. As, if we zoom out, you can see that the entire property forms a bowl-shaped depression in the ground, which, in fact, marks a singular 2,730-foot or 832-meter-wide volcanic crater in the ground known as a maar. This feature marks one of the youngest vents in a little-known volcanic field. While the exact age of the aforementioned Little Borax Lake Maar in question is uncertain, one suggestion is that it may have formed approximately 13,000 years ago in the year 11,170 BCE. Yet, as we continue to look around, you might notice several bays on the shoreline which also have a highly circular profile, with the most prominent of these being known as Horseshoe Bay. These features mark 11 maars, which each were the site of a highly explosive volcanic eruption in the last 40,000 years. In fact, at least one of these eruptions were witnessed by indigenous peoples who lived in the area during the last 15,000 years, with oral tales passed down from generation to generation telling of large explosions, the raining down of numerous large boulders of rock, and the simultaneous noise of thunder. All of these maars, cinder cones, and much more encompass a broad 300-square-mile volcanic field known as the Clear Lake Volcanic Field. While this volcanic field has not produced an eruption since the year 7080 BCE, it had erupted at an average rate of once every 1800 years between 60,000 and 10,000 years ago, and will almost certainly erupt again one day. It should thus not come as a surprise that the most productive geothermal field on the planet exists here, being powered by the heat from a massive, stationary, and cooling 1.1 million-year-old body of magma, which has a volume of 300 cubic kilometers, which at its shallowest is at 6.5 kilometers or 4 miles below sea level. But do not worry, that body of magma can't erupt and in fact is used to power numerous geothermal power plants, generating enough electricity to power 725,000 homes. Actual future eruptions in the Clear Lake volcanic field will almost certainly occur in a small area surrounding Clear Lake or in Clear Lake itself, most likely forming a maar and generating pyroclastic flows or through the formation of a cinder cone. The aforementioned pyroclastic flows and thick ashfall can theoretically reach areas up to 5 kilometers away from a vent, and to show the dangers this could pose, I have overlaid actual young pyroclastic deposits from a linked scientific paper now being referenced, presumably with all of this being in place during the last 40,000 years. While none of these maar vents are likely to ever erupt again, there is always a chance for another one to pop up somewhat close by to an existing vent in the distant future, placing nearby communities at risk. It is for this reason that the Clear Lake volcanic field is classified as a high-threat volcano. But why does this volcanic complex exist in the first place? The first thing I want to note is that the Clear Lake Complex is merely the youngest of a chain of slowly northward trending volcanic fields, the others of which are long extinct. Per a direct quote, these fields were erupted as passage of the Mendocino Triple Junction and lengthening of the San Andreas Fault opened magma pathways to the surface. As the nexus of subduction and transform movement marched northward, the age of each volcanic center approximately tracked the position of the Triple Junction and associated slab window at the time. The Clear Lake Complex has also thus trended northwards over time during its 2.1 million-year-long lifespan, almost entirely creating scattered vents which erupt once and then never erupt again, but occasionally producing larger polygenetic vents which erupt multiple times. While the early eruptions largely produced basaltic cinder cones, more viscous magma would on occasion erupt as the overall field got older and older, sometimes even including rhyolite lavas. Polygenetic centers largely constructed lava dome complexes via overlapping layers of viscous lava, constructing Cobb Mountain, Mount Hanna, and most recently Mount Canocti. These centers each produce multiple explosive eruptions, although none of them are likely to ever individually erupt again, with the last such eruption from Konocti proper and not the vents surrounding it occurring 350,000 years ago. The most recent cluster of activity in the Clear Lake volcanic field involves 6 more forming eruptions between 11,300 BCE and 7,080 BCE, with 7,080 BCE marking the date of this field's last eruption. Only a little over 100 years ago, California was the site of a major explosive eruption that was captured in this photograph. This occurred on May 22, 1915, when pressure in volatiles building beneath Lassen Peak summit broke through overlying rock, generating a powerful explosion that rapidly sent a plume of ash to an altitude of 10 kilometers or 32,800 feet. As part of the associated eruption column collapsed back to the ground due to its high density, a series of superheated pyroclastic flows quickly incinerated large swaths of adjacent forest, reaching as far as 4 miles away and incinerating a total of 3 square miles of land. Today, this area within Lassen Volcanic National Park is simply referred to as the devastated area. And yet, this was only the most recent example of an eruption from an incredibly long-lived active volcanic complex which has been intermittently erupting for 825,000 years. In that long time span, hundreds of explosive eruptions have occurred from dozens of vents, building a large-scale volcanic complex with multiple centers of activity during different periods. For reference, Lassen Peak can be found in the northern third of California, where it is 10.5 miles north-northeast of the town of Mineral. Lassen Peak is quite special, as in the vast Cascade Mountain range, it represents the southernmost active volcano in the range. Its activity is caused by the offshore subduction of the Juan de Fuca plate underneath the North American plate. The melted material from this collision then migrates upwards, intruding into the crust, which sometimes results in eventual eruptions, forming a chain of volcanoes. Before I further discuss this volcano, which contains the largest geothermal area in the entire Cascade Mountain range, I want to note a difference. Technically speaking, Lassen Peak only describes the large lava dome that produced that complex's most recent eruption, and Lassen Volcanic Center is technically the name of the broader complex. While many distinct volcanic centers have been constructed within Lassen Volcanic Center, consisting of cinder cones, lava domes, stratovolcanoes, shield volcanoes, and a caldera, its overall activity can be distinguished by 3 main phases that constructed larger edifices. The first phase of activity constructed the Rockland Center between 825,000 and 609,000 years ago via an overlapping group of dacite and rhyolite lava domes and their associated tephra. Fed by a very large magma chamber, this would lead to the largest volcanic eruption in the last several million years of the Cascade Range 609,000 years ago, ejecting 250 cubic kilometers of tephra, causing hundreds of feet thick of ash and pyroclastic flows to pile up near the volcano, and devastating an area of more than 1,000 square miles. This eruption formed a vast and deep caldera, but it is no longer visible to us today after being buried by significant amounts of more recent eruptive products. The second eruptive period occurred 590,000 to 385,000 years ago, constructing an 11,500-foot tall stratovolcano known as Brokoff Mountain via overlapping layers of basalt to dacite lavas and ash. Large volume flank eruptions occurred in the latter half of the volcano's lifespan, and it would later completely erode away due to intense hydrothermal alteration. The third period began 385,000 years ago and continues to the present, constructing many dacite lava domes in and around the modern Lassen Peak. Lassen Peak proper did not begin to form until 27,000 years ago, when a very large dacite lava dome was constructed across a prolonged eruption with a volume of 2.5 cubic kilometers. In the last 15,000 years, 6 eruptions have occurred from the Lassen Volcanic Center. The first one constructed a cinder cone and associated 3.17 square mile andesitic lava flow 13,000 years ago. In 900 CE, Dome A of the rhyolitic Chaos Crags formed in association with a tephra cone. 70 years later, it was mostly destroyed in a violent explosive eruption. Then another eruption occurred, constructing 5 more rhyolite lava domes. In 1666 CE, the cinder cone termed cinder cone formed in a mildly explosive eruption which formed many lava fountains, eventually emplacing a 3.26 square mile basaltic andesite lava flow. Lassen Peak summit then produced an eruption from 1914 to 1917, which represented its most recent activity. Since such a large area could be the site of future eruptions spanning 200 square miles, and that many of these eruptions are associated with heavy ash emissions, pyroclastic flows, and lahars, it should come as no surprise that the U.S. Geological Survey designated Lassen Peak as a very high-threat volcano. What you are looking at are the remnants of a natural disaster which once wreaked absolute devastation across the region, with this pristine landscape a decade after the disaster struck instead looking like this. In fact, if you had somehow managed to walk 50 miles to the north, west, south, or even east, you would have seen the exact same thing. No life, no trees, maybe a blade of grass or two if you were lucky, but most importantly, the largest field of degassing fumaroles on the planet, comprising tens of thousands of degassing vents which made much of the valley completely toxic to most forms of life. Fast forwarding to the present, while the area has clearly recovered and today it merely looks like a peaceful valley with a large open plain, there is a specific reason why there are no large mountains here. You see, there used to be a similar series of rugged mountains here. Then, 764,800 years ago, one of the largest volcanic eruptions to ever occur in the United States happened, causing a 20-mile-long stretch of land to subside by nearly 10,000 feet or 3 kilometers. This subsidence was caused by rock collapsing downwards to fill the empty space in what had previously been a very large and full magma chamber in a complex which is today known as the Lone Valley Caldera. So, why is there not still a giant hole in the ground, or at the very least a supermassive caldera lake such as seen at many other large calderas? The answer is that while yes, the ground did subside by up to 3,000 meters or 9,842 feet, the eruption deposits this 6-day-long ultraplane eruption generated covered this caldera by up to 1,500 meters or 4,921 feet thick of volcanic rock. And then, in the time since, up to 622 meters or 2,041 feet thick of viscous towering rhyolite lava flows were added, while at the same time, the center of this caldera has been uplifted by 400 meters or 1,212 feet. While the Lone Valley Caldera has not erupted in 16,000 years, it is still considered as an active or at the very minimum a potentially active volcano. The reason for this relates to how it behaves differently than most volcanoes, due in part to its magma chamber which holds 1,000 cubic kilometers of magma. Not only does all of this magma create dozens of fumaroles, hot springs, and even occasional geysers, but the Lone Valley Caldera was also the site of 2 failed magmatic intrusions in 1980 and 1982. Because of this, it is deemed that there is a low but still technically possible chance that this volcano could generate a small to medium-sized explosive eruption in the next millennia. Such an eruption could create a cinder cone and a mildly explosive eruption, or a rhyolite lava flow and a highly explosive Merapi-type volcanian eruption, which could even generate regional pyroclastic flows and ashfall. As a result of these hazards, with the next eruption most likely to occur near the western caldera rim of the complex, the U.S. Geological Survey designated the Lone Valley Caldera as a very high-threat volcano. Eruptions of the Lone Valley Caldera can be traced all the way back to 3.6 million years ago, when a lava dome-forming eruption emplaced a trachytecite lava flow high on a peak northeast of Laurel Mountain. Scattered regional eruptions continued for the next 500,000 years, emplacing mostly mafic vents. Eruptions then moved into the area inside the modern caldera 3.1 million years ago, although a dominant eruptive center did not emerge until 2.2 million years ago. Almost all following pre-caldera eruptions between 2.2 and 0.76 million years ago constructed a vast obsidian-rich lava dome complex known as Glass Mountain. At least 59 distinct eruptions occurred here, emplacing 100 cubic kilometers of high silica rhyolite lava. After the caldera formed in a major VEI-7 eruption, a widespread series of rhyolite lava flows covered the caldera's center, involving dozens of highly explosive eruptions across a time span of 750,000 to 640,000 years ago in primarily VEI-4 to VEI-5 events. As the underlying magma chamber was partially refilled, the center of its edifice was uplifted by more than 1,000 feet. Additional eruptions constructed more large rhyolite lava flows, such as the North Dome 525,000 years ago, Hot Creek 288,000 years ago, West Coulee 150,000 years ago, and Deer Mountain 115,000 years ago. The famous Devil's Postpile lava flow with its scenic and tall basaltic trachyandesite columns with polygon shapes formed 82,000 years ago. All eruptions since then have been far more mafic and solely occurred in the western end of the caldera, specifically constructing cinder cones and basalt to basaltic trachyandesite eruptions 66,000 years ago, 31,000 years ago, and most recently 16,000 years ago. The last eruption constructed 3 cinder cone vents, 2 spouter cone vents, several small lava flows, and a phreatic explosion crater. Within California, the most recent volcanic activity occurred on the state's most popular winter sports slope, specifically underneath a peak known as Mammoth Mountain. There, in 1989, this peak was the site of a confirmed intrusion of magma underneath its edifice, but this thankfully stalled and is today still solidifying at 9.3 miles depth. However, this failed intrusion did generate another effect, as the solidifying magma has ever since released between 150 and 300 tons of carbon dioxide each day. This has seeped into several faults and fumaroles surrounding the mountain, resulting in large areas of dead and dying trees and vegetation, which can even reach lethal concentrations in some low-lying areas. This sadly even resulted in fatalities in 2006, which is why you need to follow these guidelines shown on screen when on or around the volcano. And despite how eroded sections of Mammoth Mountain and its surroundings might appear, both of these regions have produced recent eruptions that could generate fatalities or damage if they were to occur again in the future. Specifically, Mammoth Mountain itself was last the site of 2 phreatic eruptions in the year 1252 CE, which occurred on its north flank, while its surroundings last produced a mildly explosive eruption which formed the 2 red cones south of the main edifice in the year 6500 BCE. This volcano is thus still active, having produced a volcanic eruption 64 times during its 233,000-year-long lifespan, translating to an average eruption of once every 3,641 years. 26 of these eruptions built the 4 cubic kilometer lava dome complex known as Mammoth Mountain, while 38 of these occurred at various flank vents which each only erupted once, emplacing around 8 cubic kilometers of lava and ash in the same time span. Each of these eruptions had a degree of explosiveness to them, meaning ash emissions that could disrupt regional air traffic and electrical systems, the chance for pyroclastic flows to occur from collapsing lava domes and more viscous or more explosive eruptions, and the threat of long-traveling lava flows which have flowed as much as 13 miles or 20.9 kilometers away from an erupting vent at this complex. It is for this reason, combined with the 7,200 people that live nearby and the town of Mammoth Lakes, that Mammoth Mountain is classified as a moderate threat volcano. The reason why the Mammoth Mountain volcano exists relates to the following. In California, the western portion of the state, which is a portion of the Pacific Plate, is sliding to the northwest, while the rest of the state is sliding to the southeast, which is a portion of the North American Plate. While 75% of this motion is accommodated by movement of the San Andreas Fault, a series of faults in eastern California known as the Walker Lane accommodates most of the other 25%. These Walker Lane faults serve as a path of least resistance for magma to intrude into, allowing for the creation of several closely spaced geologically recent volcanoes. As for why Mammoth Mountain is considered a separate volcano to the nearby Long Valley caldera and Mono-Inyo volcano relates to having a less alkali-rich composition, which is fairly distinct from the other two, indicating a different magmatic source for each of these three volcanoes. The first eruption from this complex occurred 233,000 years ago, emplacing a basaltic cinder cone which is now completely buried by the modern Mammoth Mountain. In fact, between 233,000 and 186,000 years ago, 18 such lava flows would be emplaced in the same general area via separate vents. The oldest lava flow beyond this area still remaining from this complex is associated with a basaltic trachyandesite cinder cone from 175,000 years ago. Additional cinder cones erupted intermittently during the following 85,000 years, with compositions ranging from basalt to dacite, and with two cinder cones producing the complex's largest lava flows 92,000 and 90,000 years ago. As for Mammoth Mountain proper, it formed through 28 primarily trachydacite but also some rhyolitic eruptions, which would overlap one another to form a steep-sided series of lava domes between 100,000 and 50,000 years ago. These lavas did not travel very far from their source, and each were up to 400 feet thick. The construction of Mammoth Mountain occurred alongside the eruption of 14 peripheral vents representing the peak eruptivity in the overall volcanic field. Activity declined thereafter, with only 7 eruptions occurring since 50,000 years ago at the locations shown on screen. 1 in 3,600. Those are the odds that the single largest volcano by volume in the entire Cascade Mountain range will erupt each year per the U.S. Geological Survey. The volcano in question is not a stratovolcano such as Mount Rainier or Mount Shasta, but rather a super large shield volcano known as Medicine Lake. Well, this vast shield volcano, which measures a whopping 50 miles long and 28 miles wide, has produced a number of geologically recent eruptions that look near identical to those of Hawaii's Mauna Loa volcano. Medicine Lake has also in the same time frame produced a series of highly explosive eruptions. As, just during the Holocene epoch, aka since the year 9700 BCE, Medicine Lake has through separate eruptions emplaced lava flows which had a composition of basalt, basaltic andesite, dacite, and rhyolite. Some of these eruptions have devastated quite large areas, with a grand total of 36.4 square miles or 94.25 square kilometers being overlaid by a layer of lava, which averaged 37.8 meters or 124 feet thick during this time span. Medicine Lake's recent eruptions have largely occurred in clusters where across a 100 to 300 year long period frequent eruptions occur, only to be followed by absolutely no eruptions for the following period of several hundred to several thousand years. 3 such recent eruptive periods emplaced lava flows from 5200 to 5100 years ago, 3200 to 3000 years ago, and 1250 to 950 years ago. This suggests that when the Medicine Lake volcano reactivates and produces its next eruption, that it will be followed by a period of heightened eruptive activity for at least the following century. While the Medicine Lake volcano during eruptions can produce volcanic hazards that include pyroclastic flows, lahars, and ashfall, its main threat are potentially long-traveling lava flows which could make their way towards several nearby communities. For example, a voluminous basalt eruption which began at a vent just south of Medicine Lake's summit area in the year 10,480 BCE would send lava flows a whopping 30 miles to the south before the eruption ended, nearly reaching what is now the modern community of Dana. Because of these hazards, the U.S. Geological Survey classified Medicine Lake as a high-threat volcano. Medicine Lake's unusually high eruptive rate during its lifespan can be owed to it being situated in a region where there is both magma generated due to the Juan de Fuca plate subduction underneath the North American plate and existing in a zone of west to east extension. This extension is situated just outside the northernmost extent of the Walker Lane region, which accommodates the majority of motion the San Andreas Fault does not accommodate, originating from the North American and Pacific plates sliding past one another. What I am trying to say is that not only is subduction occurring, but extension is providing a path of least resistance for magma to intrude into. The first eruption 500,000 years ago created an absurdly large rhyolite lava flow which measured 7.5 miles east to west, 1.2 miles north to south, and was up to 200 meters thick. While some basaltic eruptions occurred during this period, they were not common until around 300,000 years ago when the volcano entered its peak phase of activity. Frequent effusive to moderately explosive eruptions across the next 120,000 years built layer after layer of basalt and basaltic andesite lavas, creating much of the volcano's modern shield profile. Due to Medicine Lake's tall height, it at several points had thick glaciers which covered sections of its edifice. A portion of these glaciers subsequently melted during a major ultraplinian eruption 180,000 years ago, which sent pyroclastic flows a whopping 15 miles to the southwest. This eruption completely devastated the area, but most importantly caused the first part of its caldera to form. Many rainfaults were created, which subsequently erupted 3 voluminous andesite lava flows during portions of the next 80,000 years, deepening its existing caldera until it created its modern appearance. Subsequent lava flows during the most recent 100,000 years have covered nearly half of Medicine Lake's edifice, with dacite and rhyolite eruptions occurring quite rarely in clusters, specifically 30,000, 3,000, and approximately 1,000 years ago. While those of you who live in California might be aware of volcanoes such as Mount Shasta or Lassen Peak, both of these systems, oddly enough, are not the most likely volcano to erupt next in the state. For the volcano which takes this title, you would need to head east of Yosemite National Park in the eastern portion of the state. There, you would find no central towering peak, but rather a fascinating 16.8-mile or 27-kilometer-long narrow chain of volcanic vents, which almost entirely formed in the last 10,000 years. This marks the Mono-Inyo volcano, which has erupted a whopping 23 times during the Holocene epoch, with its last eruption forming obsidian-rich lava flows, massive and deep Mare explosion craters in the ground, and produced long-traveling pyroclastic flows which incinerated everything they touched. But why exactly does this volcano exist in the first place? Despite beginning inside the rim of the massive Lone Valley caldera, the Mono-Inyo volcano is not directly related to it. Instead, it merely encompasses the middle portion of a much longer 55-kilometer or 34.2-mile-long nearly straight-line chain of activity that goes from the active Mammoth Mountain complex in the south to the Mono Lake complex in the far north. These 4 volcanoes exist in a region of the state containing numerous large fault lines that accommodate the vast majority of tectonic stresses related to the North American and Pacific plates sliding past one another. This stress creates north to south trending weak zones in the crust which magma can intrude into, sometimes rising to the surface and forming a chain of incredibly viscous rhyolite lava flows. All that it took for this complex to begin was for a singular rhyolitic intrusion to occur 65,000 years ago, solidifying that area as a regional path of least resistance for subsequent intrusions to utilize. This first intrusion also resulted in an eruption, likely creating a several hundred-foot-wide crater in the ground. After pyroclastic flows scorched the nearby landscape for several miles in all directions, the eruption slowly became less and less explosive. A large rhyolite lava dome then erupted from the source vent with a viscosity 250 million times higher than that of water. Frequent partial collapses of this growing dome would generate further pyroclastic flows. After a large dome had been constructed, the eruption ended. 2 more eruptions occurred across the next 5,000 years, only to be followed by a 20,000-year gap. However, it wasn't until 15,000 years ago that the rate of eruptions in this field dramatically escalated from once every 3,333 years on average to once every 517 years on average. Here is a brief overview of the numerous eruptions which specifically occurred since the end of the last ice age. Very large rhyolite lava flows known as coulees formed during explosive eruptions in the year 500, 700, and 1200. An obsidian-rich lava dome formed in 1350. A series of explosion craters in the ground termed Mars due to the primarily steam explosions caused by shallow magma interacting with groundwater were created by eruptions in 4000 BCE, 1000 BCE, and 1350 CE. The 1350 CE vents formed the Inyo craters during the latter stages of a much larger eruption which also emplaced 3 nearby rhyolite lava flows. I also want to highlight Panum crater with the eruption that formed it in 1340 starting with a bang via a powerful explosion forming a massive 770 meter or 2,526 foot wide crater in the ground. What followed after up to 2 feet thick of ash blanketed the area was the extrusion of a thick rhyolite lava plug that would continue growing for several months. This entire aforementioned eruption in 1340 was considerably large, registering in as a 4 on the Volcanic Explosivity Index and being about 1/3 the size of the 1980 eruption of Mount St. Helens. As a result of the abundant hazards any future explosive eruptions will create, along with its high eruptive rate, are why the Mono-Inyo chain is classified as a high-threat volcano. During the last 1,000 years, what section of California do you think produced the most volcanic eruptions? Surprisingly enough, the answer is not the north-northeast of the state containing the southernmost extent of the Cascade Mountain Range. And this is despite the fact that it contains Mount Shasta, the Medicine Lake Shield Volcano, and Lassen Peak, which specifically last erupted in 1917, merely 107 years ago. Altogether, these volcanoes only erupted 6 times during the last 1,000 years. However, if we move towards the very eastern section of the state, we run into a 35-mile-long chain of activity of primarily highly viscous and explosively formed volcanic vents that stretch from several miles south of the town of Mammoth Lakes all the way north to the northwesternmost section of Mono Lake's shoreline. This chain of activity, due to variations in composition, distinct magmatic sources, and dates when they were most active, represent not 1 but 3 separate still active volcanoes. Mammoth Mountain is in the south, having erupted once in the last millennia. Mono-Inyo encompasses the middle section, having erupted 3 times in the last millennia, and the little-known Mono Lake complex lies to the north, having itself erupted 3 times in the last 1,000 years. In this entire chain, the youngest volcanic activity occurred at the aforementioned little-known Mono Lake complex, which produced an explosive volcanic eruption around 1750. And even more recently, specifically on August 17, 1890, the Mono Lake complex displayed an episode of volcanic unrest. That day, a series of earthquakes struck beneath the center of the lake, only to be seemingly followed by the brief appearance of vents degassing to such a high level from underwater that it not only rose above the lake water but also was visible from afar. This apparently occurred right next to Negat Island. While no other episodes of unrest have occurred since then, it, along with the still active fumarole and hot springs in the complex, are a reminder that the Mono Lake complex is still active. This complex will always produce explosive activity that can disrupt air traffic during the initial phase of any future eruption, along with sometimes producing Merapi-type volcanic eruptions that result in pyroclastic flows being generated. As a result, the U.S. Geological Survey designated Mono Lake as a moderate threat volcano. Before I explain how long this volcano has existed, I want to first elaborate on its most scientifically intriguing feature. Whenever a major landslide occurs, regardless of its cause or location, it leaves behind an instantly recognizable landform known as hummocky terrain. Here is an example I filmed at Mount St. Helens. There is also this example in Washington's Lake Roosevelt and at Canada's Frank Slide. In each example, you see numerous small to medium-sized hills that represent blocks or combined chunks of material deposited from a major landslide. And now, I want to bring your attention back to Mono Lake, specifically on Pahoa Island. Note the occurrence of a major landslide scarp and hummocky terrain on its western side. The area which collapsed formerly only had an average slope of 3 degrees, meaning it shouldn't have collapsed, so what happened here? The answer is that this island in the time span of less than a year during the 18th century rose by a whopping 415 feet or 126 meters. This was caused by the expansion of a northward trending magma dike that generated a cryptodome, uplifting what were lake bottom sediments and causing landslides to occur due to the uneven uplift. But since this body of magma was in spots likely less than 50 feet below ground, part of the magma eventually erupted onto the surface in the northern half of the newly formed island, emplacing a 1.15 square kilometer or 284-acre rhyolitic lava flow. Of the 4 regional volcanoes, Mono Lake is the most recently to form. With our current understanding, it did not exist in any form until 13,300 years ago. Now, the Mono Lake volcanic field consists of 30 separate vents, not all of which are necessarily accounted for by its mere 5 known dated eruptions. This suggests that some of the undated vents may be older than what this video suggests. The first eruption involved trachybasalt lava erupting at 200 meters or 656 feet depth underneath the then glacial Lake Russell, forming the Black Point cinder cone. The next 2 eruptions also occurred underwater, forming small dacite lava domes in a series of phreatic explosion craters in 100 and 1200 CE. A large rhyodacite coulee constructed Negat Island in 1400 and a cryptodome uplifted Pahoa Island, eventually giving way to a rhyolite lava flow around 1750. At this location in California, if you were to dig straight down, you would eventually hit an active body of magma at a depth of approximately 3.7 miles or 6 kilometers. On the surface, gas from the steep magma is actively being released via this very small boiling hot spring, with both the heated water and gases this vent is emitting resulting in the emplacement of yellow native sulfur mineralization on adjacent rocks. This vent is one of several which can be found at a volcanic complex in California which towers above every other regional peak. What I am referring to is the impressive active volcano known as Mount Shasta, whose summit reaches an elevation of 14,179 feet or 4,322 meters above sea level. While only weak degassing of fumaroles is present at this volcano today, do not be fooled, as this peak is the 3rd most active volcano in terms of the number of eruptions in the last 11,650 years in the entire lower 48 US states, only after Mount St. Helens and Mount Rainier. Between the end of the last ice age 11,650 years ago and the year 1250, Mount Shasta has erupted a stunning 22 times, with these eruptions ranging from small in scale all the way to large and devastating, with some greatly changing the nearby landscape. This is quite prominent via the number of young and fresh-looking lava flows, especially to Shasta's west and north-northwest. Additionally, the landscape around Shasta contains other fascinating secondary features, including a series of hundreds of closely spaced large hills which are each up to 600 feet in height. This is the story of the tallest and statistically most likely volcano in California to produce the state's next volcanic eruption. For context, Mount Shasta is located in far northern California, where it is centered about 57 miles north of the city of Redding. While many people think of Mount Shasta as only a single stratovolcano, it is in fact much more than this, as while you might only think that products from Mount Shasta can only be found on its central cone, in reality, material which used to compose the edifice of this volcano can be found as much as 36 miles away in the town of Agar. Additionally, upon closer inspection, not only does Shasta contain a series of flank lava domes and cinder cones, but it contains a vast secondary eruptive center known as Black Butte and a secondary peak known as Shastina. These 2 aforementioned features are fairly new, as they completely formed within the last 11,000 years. Long before Mount Shasta began to form, a very similar volcano stood in its place, which was constructed between 600,000 and 360,000 years ago. However, as time progressed, the western half of this volcano began to turn shades of red and yellow, indicating the hydrothermal alteration was changing hard lava and ash rock units into unstable clay. Eventually, this alteration reached such a point that all at once, 360,000 years ago, 45 cubic kilometers of the mountain collapsed in a massive landslide. Within 20 minutes, this landslide had covered approximately 285 square miles of land, where material largely moved as several hundred-foot thick blocks, forming large hills that we today refer to as hummocky terrain. The modern Mount Shasta only began to grow much later, around 250,000 years ago, and since then its eruptive activity has followed a pattern. Namely, Shasta erupts with a cluster of about 10 moderately to highly explosive eruptions across a period lasting 500 to 2,000 years, only to be followed by 3,000 to 5,000 years of very few, if any, eruptions occurring. Over the next 239,000 years, repeated Vulcanian eruptions deposited numerous layers of ash along with overlapping lobes of blocky and viscous primarily andesite lava flows. Shasta's Sargent Ridge Cone formed first and was later followed by the Misery Cone, which became the dominant center of eruptive activity for a time. Then, approximately 11,000 years ago, a powerful volcanic eruption occurred which was 84% larger than the 1980 eruption of Mount St. Helens. This eruption notably generated sizable volumes of pumice while also incinerating large swaths of forest up to a distance of 8 miles from its summit cone, which retain a grey tint to this day. The aforementioned eruption, along with a few subsequent smaller eruptions during the next few hundred years, eventually led to the creation of a brand new 13.5 cubic kilometer lava dome complex known as Shastina. Only 100 years after Shastina stopped erupting, activity temporarily shifted 7.2 miles to the west-southwest, building a 2,400-foot tall dacite lava dome known as the Black Butte. Activity then shifted back to create the brand new Hotlam Cone around 8,000 years ago, with eruptions from this vent over the next several thousand years occasionally emplacing flank lava flows, but largely producing ash-rich eruptions. The last two such eruptions from this volcano occurred in the early and mid-13th century. While we do not know when Shasta will erupt again, the rate of recent eruptions suggests a yearly chance of an eruption is about 1 in 530. This is the hazard map for Mount Shasta were an eruption to occur, and due to the presence of glaciers along with heavy ashfall any future eruption would likely bring, the main threat would be long-distance lahars that have the potential to severely damage certain areas up to 36 miles away from the volcano's summit, although pyroclastic flows that could travel several miles would also be a danger. These hazards are why Mount Shasta ranks as the 5th highest threat volcano in the United States, ranking in as a very high threat volcano. Unknown to many, there is an active volcano in Southern California, hence these degassing fumaroles and mudpots which are releasing carbon dioxide, sulfur dioxide, and hydrogen sulfide. These gases being emitted originate from a still active and partially liquid body of magma that exists at several miles depth beneath the southeast corner of the Salton Sea. This magma has heated overlying ground to such an extent that it is utilized via 11 active geothermal power plants to generate electricity for more than 400,000 and soon by 2027 up to 705,000 homes. Thus, with such a vast energy source located underground, you might be curious why, if you look around, that you do not see a towering nearby stratovolcano or obvious central volcanic vent. The reason for this is that the volcano in question, known as the Salton Buttes, is one of the smallest volcanoes on the entire planet by both area and volume erupted. However, small does not mean less dangerous, which is why I present to you the fascinating story of the Salton Buttes volcano, whose highest point is 131 feet or 40 meters below sea level. Yet, due to the topography of the region, this is not a submarine volcano existing entirely on land, although I must admit that these spectacular geothermal vents being shown here were all underwater up until 2006. As an overview, the Salton Buttes volcano contains a dispersed group of 5 small lava domes which formed in 3 separate volcanic eruptions which all occurred within the last 3,000 years. Lava domes are a distinct type of volcano created by incredibly viscous flows of lava which are unable to travel very far from their source and thus pile up around the erupting vent to naturally form a steep side dome of material that can grow to be as much as hundreds or even thousands of feet tall. In the case of the Salton Buttes, these 5 lava domes were all constructed out of rhyolite lava, the most silica-rich and viscous type of lava that exists on our planet. In other words, involving a type of lava 2,500 times more viscous than a typical basaltic lava flow produced by Hawaii's Kilauea volcano. The aforementioned 5 lava domes have quite a small volume altogether, but each formed in explosive eruptions. Mullet Island was the first lava dome to form in a weakly explosive eruption in 950 BCE, only to be followed 40 years later by the formation of the magnificent Obsidian Butte lava dome in 910 BCE in a more explosive eruption that likely even generated pyroclastic flows. Then, possibly involving 2 closely spaced separate eruptions or one continuous longer eruptive sequence, the North Red Hill, South Red Hill, and Rock Hill lava domes all erupted in the year 200 CE. This last sequence was also fairly explosive, likely registering on the Volcanic Explosivity Index as a 2. While no eruptions or shallow intrusions of magma have occurred in the years since, this area has remained quite seismically active, generating frequent earthquake swarms in association with an area known as the Brawley Seismic Zone. This zone marks a major tectonic plate boundary between the North American plate to the east and the Pacific plate to the west that connects the southernmost extent of the San Andreas Fault to the Imperial Fault. This entire zone serves as a pull-apart basin related to the motion of these 2 tectonic plates, allowing for occasional batches of magma to rise into the crust, interact and mix with ancient solidified granitic intrusions, and then erupt as rhyolite lava. Any future eruption of this complex would also be explosive, primarily due to gas having an incredibly difficult time escaping absurdly viscous lava. Thus, the gas would build up in pressure until it cracked overlying rock, exploding upwards, generating a plume of ash and pyroclastic flows. Falling and ejected pumice would also be a hazard within a mile of an erupting vent, and ash accumulations thick enough to cause problems, and possibly even damage could occur up to 5 miles away from an erupting vent. These hazards, combined with the more than 2,500 people that live in the hazard zone of this seemingly small volcano, are why the Salton Buttes is classified as a high-threat volcano. A mere 2,174 years ago, Death Valley was the site of a catastrophic explosion. As, while unknown to many, Death Valley within California, which often ranks among the world's hottest locations, is surprisingly also host to a singular active volcano. This volcano consists of a chain of 14 large and deep explosion craters in the ground, the largest of which measures a whopping half a mile long, 2,450 feet wide, and 722 feet deep. To understand the sheer power of the blast that formed the largest crater of the Ubehebe Craters volcano, I will compare it side by side to that of Sedan Crater. Sedan Crater formed as the result of an underground 104 kiloton nuclear blast in 1962. And yet, Ubehebe Crater, which formed due to an explosion at a similar depth, is even larger than that massive aforementioned crater. Today, it is completely safe to visit this volcano as it currently shows no signs of life, involving 0 hot springs, 0 fumaroles, and 0 volcanic earthquakes. While the specific cluster of Mars itself is unlikely to ever erupt again, the conditions do exist for a future eruption to occur somewhere within a 6-mile radius of this spot. Such a future eruption would almost certainly also be explosive, meaning it would disrupt regional air traffic and pose the threat of generating up to 10-kilometer-long pyroclastic flows. As a result of this threat and the potential that it could erupt again, Ubehebe Craters is classified as an active volcano and is listed by the U.S. Geological Survey specifically as a moderate threat volcano. If we zoom out from these craters ever so slightly and head just 3 miles to the west, there are a series of highly eroded monogenetic volcanic cones and their associated lava flows. Note how these several million-year-old features seemingly exist along 3 north-to-south trends, which in actuality represent now largely or completely inactive fault lines such as this feature here. And now, going back to the Ubehebe crater, there is also a fault line that extends along the crater's longest orientation, hence the color difference in rock units seen in this image. Both of these features, despite forming millions of years apart, formed due to the same geologic setting which could one day power a similar future eruption. These faults formed due to the intersection of 2 tectonic provinces, the Basin and Range and the Walker Lane. The Walker Lane is a series of faults that accommodates the vast majority of the region's tectonic plate motion not accommodated by the San Andreas Fault. Meanwhile, the Basin Range represents a broad area where the crust is slowly spreading apart, forming many fault lines. The created fault lines from this motion serve as weak spots in the crust that allow for magma to intrude into the crust on occasion and sometimes produce volcanic eruptions. At Ubehebe, this occurred through the Tin Mountain Fault. In approximately the year 150 BCE, a medium-sized batch of magma intruded into the crust, working its way up the aforementioned fault line and generating a swarm of earthquakes. As gas bubbles in the rising molten rock expanded, it further propelled the basaltic magma upwards, causing it to finally erupt onto the surface in a mildly explosive manner. For the first few days, this slowly built a cinder cone which continued to produce sustained low-altitude ash emissions and strombolian explosions. While this was occurring, shallow magma ran underground to the west, transferring heat to underlying groundwater. This groundwater flashed to steam, causing it to expand in volume by a factor of 1600 until the pressure became so great that it exploded and broke through overlying rock, generating larger ash plumes and multiple several hundred-foot-wide mark craters in the ground. As the cinder cone continued growing, the underlying magma dike expanded southwards where there was even more groundwater, causing a series of larger and larger explosions to occur over time. Heavy rainfall subsequently filled one of these craters, causing repeated explosions within it to form the Little Habe Tuff Cone. However, since these explosions blew off the top half of the existing cinder cone which had formed, collapsed material blocked its magma conduit. Magma then spread out laterally underground, causing the largest batch of groundwater so far to flush to steam, build in pressure, and explode upwards with the force of many thousand tons of TNT. As a 14-kilometer-high eruption column was blasted high into the atmosphere, part of the eruption column was so dense that it collapsed back to the ground, generating a series of 200 degrees Celsius pyroclastic flows which scorched the surrounding landscape in all directions, albeit preferentially downslope. This pyroclastic flow would continue running out to 9 kilometers or 5.6 miles away, by which time it had scorched an area of 20 square miles. And this is how the fascinating Ubehebe Craters volcano formed.